The problem of Lab 3 was to experimentally measure how the magnetic field of a bar magnet changes with distance, then compare this to the result predicted by the Biot-Savart law, and calculate the magnetic moment of the magnet. From my results, I found that the magnetic field at a 45-degree angle at a distance of 0.20035 meters experimentally was 7.5 times 10 to the negative fifth Teslas in the x direction and 5.02 times 10 to the negative fifth Teslas in the y direction. And we'll see later that this is quite different than the value we calculated computationally. And my mu was found to be 0.488 times meter squared. So this lab was performed by using a magnetometer app on my smartphone to determine the distance from the bar magnet when the magnetic field equaled specific magnitudes, and we tested this at different increments of magnitudes of the magnetic field. And so I determined that the magnetometer on my phone was in the upper left-hand corner, and we repeated this procedure for observation points both on axis and at an angle of 45 degrees from the magnet, and I performed it outside to minimize other magnetic fields. Prior to the lab, I predicted that the magnitude of the magnetic field would fall off like 1 over the distance cubed, and that field would look something like the one shown in the picture on the right here on the screen, and the strength being off-axis being less than the strength of the field on-axis, and this is what I found in my results. So as expected, the observation point became closer to the bar. As the observation point became closer to the bar magnet, the field strength increased quickly, and so when the magnetometer was far away from the magnet, it measured a near zero magnetic field in the x direction, but as it moved closer, that x component increased. And so in the next sections of the lab, I'll go over the physics principles involved, analyze my results, and go over the model I used to represent the system. For the physics principles involved, we looked at magnetic dipoles and magnetic dipole moments. The bar magnet is a permanent dipole with the dipole moment pointing in the direction of the magnetic field, and we calculated this value of the magnetic moment of the bar magnet. With magnetic fields, the bar magnet created a steady magnetic field, and this is what we measured, allowing us to do our calculations. For the distance dependence and the field strength of the bar's magnet field is proportional to 1 over r cubed, which is similar to what we found experimentally. And for superposition of magnetic fields, the magnetic fields of the Earth and bar magnet superimpose, so to account for this, we had to align our phone's magnetometer so that the magnetic field of the bar magnet was orthogonal to the Earth's magnetic field, and that allowed us to measure the bar's magnetic field separately. And then we then had to adjust our measured values for the y component similarly. So here you can see my results. We have our distance values here for the magnetic field strength here, and we graphed the natural log of these values here to get the relationship, and we can see a good correlation here on the graph. So our slope is the n, so the exponent with the relationship of the distance to the field strength, and that should be around -3, so that's good results here. And then this y-intercept represents the natural log of k, and so here you can see that we used k and then found mu using this equation, and this is the overall equation here for the magnitude of the magnetic field of the bar magnet. And so when we analyzed it computationally with the magnetic field at a 45-degree distance, we see that there is quite a difference in the values calculated here, and this is due to several things. One, interference from other magnetic fields is possible, limitation of the tools we had in the lab, and then experimental error. So you can see there's quite a big error, although our results did overall show a good relationship. So our results continued. We see here the results for the perpendicular off-axis field, and you can see here we had to correct for the y component because of that superposition of the fields. So here's my model. Here the white cylinder represents the bar magnet, and its magnetic moment is pointing in the positive x direction. The orange arrows represent the on-axis field, and the blue arrows represent the perpendicular field. And then the pink magenta represent the field at the 45 degrees. So note how the orange arrows are twice as long as the blue, because the field strength is twice as big on-axis as compared to perpendicular, based on the equations we have. And so the field strength is weakest over here at 45 degrees because that is the farthest distance away from the magnet. And so this model also shows the direction of the field. Note how the field kind of loops around like here. The orange arrows are pointing to the positive x, whereas the blue arrows are pointing in the opposite direction, the negative x. And so and then you can see our pink arrows are pointing in. So to calculate the magnetic field of these observation locations, the code takes in our data and calculates the field at each specific point based on this equation. So you can see here's the written out equation mathematically, and then here is the equation in Python, and then here is the code for my arrows. And so, yeah, you can see that here, this is a very good visualization of the magnetic field, and yeah. So, for conceptual questions, if I hadn't oriented my experiment to compensate for the magnetic north, my results would have changed because the fields would superimposed, meaning the magnitudes recorded for the magnetic field would be larger, and results would not be accurate because the fields would be superimposing. And if I were to stick the two identical magnets together, the strength of the field would roughly double if the magnets were pointed in the same direction, and would roughly cancel again based on principal superposition. And so in this lab, we learned a lot about permanent magnetic dipoles and the behavior of the magnetic field of a bar magnet, and the results generally show the expected behaviors, but experimental errors played a large role. Thank you.